Thank you, everybody. Thank you. This is wonderful to be here. Thank you, Shin and Liva. This is a great opportunity. I see many faces, or people, especially from Mellanox. I only met you on phone calls. Very nice to see you here in person. So, okay. So I'm going to talk a little bit about RDMA on SONiC. This talk is unfortunately more RDMA than SONiC, but I think you guys are all networking engineers, and I think hopefully we'll have something interesting to say. Okay. So very briefly, if you are not familiar with RDMA, it essentially transfers data directly between servers without burning CPU cores. We use RDMA in Azure for storage-related traffic, and it's over 65% of our network traffic, either in bytes or packets. We use it within DCs, within our data centers. We also use it between data centers, and when you go between data centers, we go over up to 100 kilometers. So it's a massive, very scaled-out effort. Okay? And this scale is made possible by many innovations. DCQCN, something that we built together with Mellanox several years ago. And RDMA has reduced our COGS because it saves CPUs. It reduces latency for our users. It reduces jitter. Essentially, it's critical for all high-performance workloads. And we always run RDMA over Ethernet, right? It's essentially RoCE. When we say RDMA in the context of this talk, it's RoCE. It's not InfiniBand, okay? Just to be clear. If you have a basic Ethernet router, what do you need to support RDMA? In Microsoft, we essentially use layer 3 routing. Our scale is too big for just pure layer 2 routing. So we need to provide DHCP-based class profiles. ECN and PFC are integral. PFC is required to make Ethernet lossless. ECN is an integral part of our DCQCN congestion control support. We obviously need flexible buffer allocation. RDMA is all about managing buffers on the routers. Performance tuning and all of that is done essentially by managing the buffers because it's a lossless protocol. PFC watchdog is needed for critical when deadlocks happen, and we'll go into that in a little bit more detail. And obviously, because you're going to reserve a certain number of queues, 2 in our case, you need per queue telemetry, right? You can't just have general number of packets in and out. You need to know how many of them were RDMA, which queue, what happened. So all of this telemetry is needed. The key thing I want to point out is all of this is available by default in SONiC, comes built in, and we have worked very hard to tune the values to the best that are known. Obviously, much of the tuning has been in the context of Azure, so that goes without saying, but all of this is available by default in SONiC. So that's great, but that's basic support that's going to be available in any network operating systems. So that's not very surprising, right? But there is a whole bunch of advanced features, right? The key that I'm going to talk about today is dual-ToR support, and how that can lead to deadlocks, and what did we work on. Essentially, the priority change and bounce back, that is a key feature that SONiC team and RDMA team in Microsoft work together. I'll spend most of the time talking about that. And if time permits, the next 3 ones, essentially streaming telemetry for key watermarks, automatic detection of headroom blowout, and something that's kind of close to my heart, but we haven't succeeded very much, is automatic buffer tuning, right? So if time permits, very, very briefly, I'll mention the top 3, but most of the talk is about the top one. Okay, so we'll see how we do on time, and we'll go from that. Okay, so there's a very brief primer on dual-ToR setup in Microsoft that's kind of rolling out. So you have the wider network, and then we are going to talk about T1 down. Okay, so you have a layer of T1 switches, and there are 2 tier 0 switches on top of the rack switches. We just call them upper T0 and lower T0, UT0 and LT0. Can be either active-passive, or it can be active-active. It doesn't really matter. The key thing is server only has 1 IP address. Okay, server has 1 IP address, and T0 announces VLAN to T1. It doesn't announce the specifics. That's the key thing. So that way, nothing changes as far as the server is concerned. And then obviously, there is ECMP routing that's happening from T1 on. Because of that, what happens is when T1 sends a packet, it can go to a standby service. And let me show you a little animation to make this clear, right? So initially, both UT0 and LT0 are active. When the packet comes, it may go to LT0 and eventually reach the server this way, okay? But if, now imagine, for example, that the connection between this particular server and LT0 is out, the way the packet is going to go is going to come from top, it's going to go to LT0, it's going to bounce it back, and it's going to go via UT0, it's going to reach the server, right? That's the advantage of dual-ToR. Your fault domain becomes localized to the server. You are not dependent on whether one of your T0s is active, whether that wire is active or something like that. What happened here, though, if you noticed, we went from valley-free routing to valley routing, right? Typically, in a data center, you have valley-free routing. Your packet goes up from T0 to T1 to T2 or whatever it might be, and then it starts coming down. Never changes direction. It's just up, you change direction once, you come down. In this particular case, unfortunately, you went up, you came down, you went back up again. So that's valley routing, and the InfiniBand community has known this for a very long time. Valley routing and credit-based flow controls do not mix very well, right? Same thing happens. There is nothing particularly fancy here. Valley routing can cause PSC deadlock, okay? Deadlock essentially requires cyclic buffer dependency. That's just a simple picture. It shows that switch A can pause switch B, B can pause C, C can pause A. You will have a deadlock like this. This looks like you have a routing loop, but you can do this without actually inducing routing loops, okay? This is, again, all of this is pretty well known. InfiniBand community has known this for a long time, right? Deadlock requires cyclic buffer dependency. Cyclic buffer dependency can arise out of valley routing. It's rare, okay? You will see how complicated of a setup you require. The trouble is when you're at Azure scale, anything bad that can happen is practically guaranteed to happen, and potentially multiple times a day, right? At our scale, everything that bad that can happen always happens. We all know that, right? So here is a little illustration. Let me see if I can make sense of this, okay? So there are two flows here. There is a red flow that goes from P to Q, and it's essentially bouncing back. It goes from 1 to 4 to 2B, right? It's bouncing back to 5 and coming down to Q, all right? And there is a blue flow, which goes in the opposite direction. It's going from R to S, okay? So notice that Q and S are destinations that are under the same rack. This is one of the many scenarios. This is probably the simplest scenario. Even this is a little bit complicated, okay? And now we'll assume that we have this bounce back, and this is how it's set up, okay? So this is the flow. This is how your traffic is flowing because particular links are down. Can happen. Okay, now what? Now let's pretend that there is a little bit of congestion here, okay? This can happen because there is another flow, could be anything, temporary burst. Once this happens, your pauses are gonna start spreading, okay? You're gonna have pauses that go back to where these flows came from. They're gonna start cascading, 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 and back. You have a deadlock, okay? So this is essentially just, and this happened strictly because of valley routing, okay? Once you have this kind of deadlock, you're dead because routing loops or any of these things are temporary, but ultimately once you have a deadlock, that condition remains, even if the corresponding traffic flows stop, right? Because PFCs are flowing, your packets are lodged into the buffer is not draining, we have a deadlock, that's it, okay? So shorter version of this is your credit loop, okay? You have a very simple credit loop here. I thinned out the lines that are not needed. You basically have a simple credit loop that goes from 2B to 5 to 2A to 4 to 2B. This is just gonna circulate like this. Once you have, this is how you get a credit loop without a routing loop. This is happening because there is valley routing. Valley routing happens because of dual-ToR, and now we have to do something about it. So what can you do? Well, deadlock is very detrimental to RDMA performance. I talked about PSC watchdog. Once the font watchdog has to fire, it has to break deadlock. The only way to do this, if the deadlock forms, is to essentially drop a whole bunch of packets. You pick essentially a victim side, randomly drop packets. This is standard how deadlock control is done in any distributed system. Can we prevent deadlock, right? We can, and we have thought about this quite a bit, and it's actually kind of simple. All you have to do is to make sure that when you bounce the packets, they go on the different priority, and that automatically avoids the loop. It's very simple. You have essentially packets flowing on the same priority. If you avoid the, on one direction you go back in a different priority, you'll avoid the loop. Essentially break cyclic dependency, prevents the deadlock from forming. And let me see if I can explain this. We'll go back to our same example again. I'm gonna make things a little bit more complicated here now. I'm gonna use solid lines for one flow and dotted lines for another flow because now I need the color for changing the bounce back priority. So if you have this, we'll start again. Now let's pretend that when we bounce back, we change the priority from green to red, okay? Solid line is one flow, dotted line is second flow, bounce back is green, all right? So once you start, we have a congestion here. You're gonna get these pause frames. But now, in this particular case, remember that some pause frames are going on green, some are going on red. And that's essentially what saves you. The green from 4 to 2 2 is going to start pausing this back on red. Okay? That's essentially what breaks the deadlock. Okay? You no longer have a circuit buffer dependency, and as a result, you're not going to have a deadlock. Okay? So this is all easier said than done, and Guhan can tell you a lot more about all the pain when we went through here in implementation. Ying is also here. It was a massive amount of effort. Okay? So what do? We essentially remap the bounce traffic to another queue. Okay? So when packets arrive on tier 0 and 3, and if they're, and only if they're to be bounced back, they're bounced back on 2. And this is essentially achieved via tunneling, and we change the priorities, right? And similarly, 4 is mapped to 6. The mapping 3 to 2, 4 to 6, this is all Azure specific. You can set up any values you want. This was a joint implementation with SONiC team and several ASIC vendors. There's a high-level description. There is a link for that. And there is a white paper that kind of talks about what are the different pros and cons and what are the various other things we could have done. This, in fact, you can extend for multiple bounce back. This is only one bounce back. In theory, you can extend multiple bounce back. We don't do that. You can do it if you want. Okay? It's all available by default in SONiC. Okay? And this is kind of the power of having our own in-house operating system. This is a problem that is unique to a very large doing RDMA, and RDMA deployment and dual-ToR. Not everybody does this, and since we are able to do this, we have, the SONiC is open source, we are able to take advantage of that and implement a solution like this. Okay, so you're doing kind of okay on time here, right? So this is available by default on SONiC. I'm happy to answer more questions. If something was not clear, I know this is kind of, everybody doesn't think about, these guys think about deadlock all the time. I know the Mellanox people do, certainly. But if you guys don't, happy to talk to you more about this, okay? So what's the takeaway here? We basically use RDMA to lower our cost and improve performance. It's primarily used for storage traffic today. Huge amount of our traffic goes on RDMA. SONiC is configured and ready for RDMA out of the box, offers many advanced features like PCBB support for dual-ToR. There are many others in the pipeline. Looks like I have some time, so I'm happy to answer questions, or I can briefly talk about some of the other ideas. Your choice. Anybody has questions? I can take those, or I can talk about other things. There is time. I don't know, I have 15 minutes, right? So we have 2 or 3 minutes left? Yeah. Yeah.
Are there other cases where you have bounce back by design and not because of routing?
Not because of dual-ToR, you mean? Or not because of RDMA? Sorry. I didn't actually quite understand what you said. I'm asking you. Yeah.
So do you have other cases where you do bounce back by design?
There are oh, sorry, I have to be here. Okay. Yes. There are a couple of small cases in Azure where we may do bounce back by design. There was, it's kind of hard to explain that without a whiteboard. But yeah, they're much rarer, okay? And our determination was that, and they happen only in error case, okay? So think about this. This is an expensive feature to implement, right? Expensive in the case of its coding complexity, and instead of our monitoring software has to change because we are monitoring 2 queues before, now we have to monitor 4 queues and all that, right? So it's kind of expensive to do. We decided that we would take a chance on bounce back, potentially causing deadlock, and then broken by PSC washout. So that was okay. But in case of dual-ToR, that valley routing is going to happen more and more. I mean, that's the whole point, right? You don't want, why did we put 2 TORs there? So that we can bounce the packets back if needed. So it would happen, the determination was that it would happen more often, and hence we implemented PCBB. So, yeah.
How detection happens? Is it purely based on what stop time was expired? Or, say in your diagram, right? So you have 3 boxes.
Yeah.
So are you running any protocol there to figure out, indeed it's a deadlock?
So no, okay, so here's the thing. If you run PCBB, deadlock will not happen, period. It's a deadlock prevention system. It's not detection. Deadlock will not happen by design, okay? So that's the end of that. Deadlock will not happen. If deadlock happens, we can detect it priority, the PFC watchdog, basically you watch a queue not making any progress. You see PFCs flowing, but a queue not making any progress, at which point you know that the queue is stuck. And then you fire the PFC watchdog. But if you implemented PCBB, if PCBB is operational in dual-ToR scenario, there will be no deadlock. Yeah.
So how much extra bandwidth do you guys provision for bounce back?
So think about this. It doesn't have to be that much extra, right? Because those wires are still there. And you're not going to have to provision unnecessarily extra traffic. It's not going to be much, right? Because the packets that are flowing, the T1 bandwidth is doubled anyways because you have two T0s and they're double the uplinks. When the packet comes down, yes, there is one bounce back bandwidth. So potentially, in the absolute worst case, you can say it would be 50% more. But it's not going to be like that. Bounce back will be rare, and the T0, T1 links are doubled anyways. So.
Yeah, from which release do you have implemented RDMA?
Sorry?
Which release in SONiC? 2020, 2021?
This is a good question. Go on. when is PCBB available?
During the
Yeah.
2012.
Yeah, it's available starting 2012.
Yeah, that's.
So maybe the question about RDMA specifically or RDMA with PCBB? I think the Jitu is.
So RDMA has been available since
For- yeah.
2018. That's not a problem.
Yeah.
The PCBB feature is new, and that's what Guan was talking about. Yeah. Good. Okay. More?
No more questions from online. Thank you.
Okay. Thank you. Thank you.